This lecture is about the issue of imbalanced data and its effect on classification. Imbalanced data refers to a classification problem where the classes are not represented equally. One of the assumptions of machine learning classifiers is that datasets have balanced class distributions, so these algorithms tend to struggle when faced with imbalanced classification data. That happens basically because with imbalanced datasets, a machine learning algorithm doesn't get the necessary information about the minority class to make an accurate prediction. There are several sampling methods to deal with imbalanced datasets. In general, these methods aim to modify an imbalanced data into a balanced distribution by altering the size of the original dataset. When working with imbalanced data, using the overall accuracy as the performance metric can be misleading as minority classes hold a small effect on this measure. Therefore, for a better insight, it is recommended to analyze other metrics that are more suitable for accuracy assessment in these situations, such as precision, recall, or the F-score. So we're going to use our remote sensing data example to analyze how classification is influenced by imbalanced data. First, we use the raster package to import the surface reflectance bands for a Landsat image that I download from the USGS Earth Explorer. I'm also importing into R a polygon shapefile containing the training data. Next, we extract the training data from the image bands, which results in a data frame containing the extracted training values for each of the 6 reflectance bands plus the class attribute. Then we create a training test partition to build a training set and a testing set, with 70% of data going to training. We see that class 2 is the majority class. It has about 6 times more observations than the classes 6 or 7, which can be considered minority classes. So the training set is the largest of the datasets. It has more than 56,000 samples, while the test set has more than 24,000 samples. For the purpose of this exercise, I'm going to use a fraction of that data, only 2,400 observations. We see that the proportion of classes is the same as before. We then build a model to predict class using a subset of reflectance bands. Here I use method equal RandomForests and assess accuracy based on training error rate. So the accuracy for this model was 0.979. Okay, so our goal now is to create a balanced data set so we can compare the accuracies between the two types of datasets. One of the sampling methods for balancing data distribution is subsampling. I wrote this function, which basically asks for a data frame, a class identifier column, and a desired number of samples for each class, and retrieves a new data frame with the same number of observations in each class. In this case, we are asking for 400 samples in each class of the training dataset. And here we obtain effectively a balanced dataset. When fitting a random forest model, we find that the resulting accuracy was slightly higher with the balanced dataset than with the imbalanced one. We can preferably evaluate the performance of both models using the testing set, as it is an independent set of data, not used for previous training. We see that the overall accuracy of the imbalanced model was higher than that of the balanced model, which is explained by the uneven proportion of classes in the testing dataset. This result shows the effect of the larger proportion of the majority class on the overall accuracy measure. As the overall accuracy can be misleading as performance metric, it is advisable to evaluate other measures. Here I'm using sensitivity, which is also known as producer's accuracy in remote sensing. We see that the producer's accuracy of class 2 was lower in the balanced model than in the imbalanced model. In contrast, class 7, a minority class, had a higher producer's accuracy in the balanced model than in the imbalanced one. This result shows how these machine learning algorithms are accuracy driven. In the balanced dataset, errors from class 7 have the same cost as those from class 2, which leads the algorithm to search for maximizing accuracy of all classes in a more balanced way. In these links, you will find further advising for dealing with imbalanced datasets. For a detailed description of the examples shown in these slides, I invite you to read the post in my blog. You'll also find all the links in the description section of this video. Thanks for watching, and don't forget to subscribe to my YouTube channel.